Hey everybody. Now that we've got a handle on some of the basic physics of motion and gravity, we can start to really understand the motion of planets and how people figured out the motion of planets. And ironically, people actually figured out how planets move around the sun before anybody knew why. Simply by watching the planets. And so this era in astronomical history is usually called the Copernican Revolution, for reasons we'll see here in a second. But just to recap what we've been talking about before, going back to ancient Greece, people concluded that the Earth is stationary because they couldn't see the parallax of stars with the naked eye. That the inability to see parallax implied to them that the Earth must not be moving around the sun, and if the Earth isn't moving around the sun, then the Earth is stationary at the center of the universe, and everything must revolve around the sun, or must revolve around the Earth. And that was the end of the story. That settled the debate for the better part of 2,000 years. But even beginning in ancient Greece, people noticed a problem. If the planets revolve around the Earth, and the Earth is the stationary center of the universe, then you'd expect that the planets would be moving in one direction, that the planets would just always be moving eastward, 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 eastward around the Earth as they revolve around the Earth. And people noticed fairly quickly that planets usually move eastward around the Earth, but actually what they do is, every now and then, planets will move eastward, 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 eastward. They'll come to a stop, they'll slow down and come to a stop, move backwards for a while, that is to say, move westward, slow down again, and then start moving eastward again. And nobody really had a great way to explain why they do that. There were plenty of astronomers that came up with ideas to try to explain it, but nobody had a great explanation. If the planets are supposed to be going around the Earth, why do they occasionally slow down, move backwards, and then keep on going eastward again? This occasional westward loop is usually called retrograde motion. Retrograde, in this case, just means backwards, right? Most of the time, the planets are moving forwards, but every once in a while, they'll just stop, move backwards for a few months, stop again, and then keep moving eastward again. Why should they do that? Nobody had a great explanation. Not for lack of trying, though. So flash forward to the 16th century now. So again, this is about 2,000 years later. An astronomer by the name of Nicholas Copernicus comes out and says, well, you know, I have an explanation. I have a possible explanation for why the planets move retrograde. But it requires you thinking that the Earth and all the planets go around the sun and not around the Earth. What Copernicus says is, if the Earth and all the planets, like Mars, if they orbit around the sun, then what you're actually seeing as the Earth and Mars, in this case, as they come into alignment, as the sun, the Earth, and Mars come into alignment, Earth's moving like this from 1, 2, 3, Mars is moving here, 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 and so from our point of view, from the Earth's point of view, well, what do we see here on Earth? Well, Mars is here relative to the background stars, and then Mars moves here, and Mars moves here, so Mars is moving eastward, eastward, eastward. But then as Earth and Mars come into alignment with the sun, Earth actually passes Mars. And so since Earth is passing Mars in its orbit, Mars appears to fall behind from 3 to 4 to 5. And then as they come out of alignment, Earth is moving around the sun, but Mars is moving around the sun, and from Earth's point of view, Mars starts moving eastward again. So Copernicus makes the argument, well, this is a much simpler explanation. All you've got to do is think that the planets go around the sun and not the Earth, and that explains the retrograde motion. Actually, Copernicus goes one better and says, well, when the sun, the Earth, and Mars are in alignment like this, not only is that right in the middle of retrograde motion, but also the sun and Mars are on opposite sides of the Earth. So this alignment of the sun and the planets is what's called opposition, where from Earth's point of view, Mars and the sun are on clear opposite sides of the sky, 180 degrees apart. So that when the sun is setting, Mars is rising, and when Mars is setting, the sun is rising. From ancient Greece through the Roman Empire and the Dark Ages and into the Renaissance, people thought, well, that the planets are going around the Earth and they just occasionally will stop and go backwards. And if you asked somebody, well, why is it? In this instance, in this calendar, September 1st is not just the middle of retrograde motion, it's also when Mars is opposite the sun. And if you asked an astronomer for all of those millennia, well, why is it? Why is it that retrograde motion always coincides with opposition? Why do they always happen at the same time? An astronomer would say, well, I don't know, it's just a coincidence. It's just the way things work out. Where Copernicus comes and says, oh no, it's not a coincidence that opposition and retrograde motion happen at the same time. That the retrograde motion is happening because the planets are in alignment, because Mars is in opposition. That's exactly why Mars appears to be falling behind. And Copernicus publishes his book, saying, well, here's a nice idea, right? Copernicus's argument, saying that the planets go around the sun, is mostly based on aesthetics. It's mostly based on, isn't this a nice, simple, pretty explanation for the motion of the planets? He doesn't have proof. He doesn't really have surefire evidence that says, oh no, the planets must be going around the sun, and they must not be going around the Earth. People had been observing the planets for a couple thousand years, and nothing that they saw, except for maybe the retrograde motion, nothing they saw really made them doubt that the planets moved around the Earth. So Copernicus's book is mostly saying, well, here's this idea, it is simple, it's elegant, it's nice, and it explains retrograde motion, and it also explains why retrograde motion happens at the same time as opposition. I think this is a nice idea. Copernicus publishes his book, and he dies shortly thereafter. So Copernicus wasn't alive to push his book into people's hands and say, my idea is true, the planets do go around the sun. So when Copernicus's book came out, most people who read it were not instantly persuaded. It's not like everybody changed their minds immediately. I mean, there were a lot of people that were given pause by the social, political, or religious implications of the Earth not being the center of the universe, but even those people who were not reticent for those reasons, even people that were more scientifically minded, most of them read Copernicus's book and they thought, okay, yes, that is a nicer, simpler explanation, but where's the proof? Where's the evidence? And so most people read it and discarded it. Some people read Copernicus's book and they thought he was onto something, just what he needed was the evidence to back it up. And so they decided they were going to be the ones to go and find the evidence. So Tycho Brahe was a wealthy nobleman in Denmark, I want to say. And he's got some money. He decides astronomy's going to be his hobby, and so he pays his money, and he gets his friend, who was the king of Denmark at the time, to put up some money to build an observatory. Of course, this was just before the invention of telescopes. So Tycho Brahe's observatory was a naked eye observatory, a building with towers and an open roof, where Tycho Brahe and his assistants would, by the naked eye, watch and record the motions of the stars and the planets and the sun and the moon every night. Every night. For 25 years. And after years and years and years of collecting the observations, just watching, by eye, watching the motion of the planets relative to the background stars, he had these huge volumes and volumes of measurements, just essentially spreadsheets before that was the thing. The problem is, Tycho Brahe didn't know what to do with it. Brahe was a rich dilettante. He was an amateur. And he needed somebody that could actually do the math and knew something about astronomy to figure out what to do with all of this data that he had collected. So Tycho Brahe hires Johannes Kepler, who was a German right out of college, and Kepler was trained to be a priest because, well, everybody who was getting an education back then was basically being trained to be a priest. But Kepler had an aptitude for astronomy and math and decided, do I want to go into the priesthood, or do I want to get paid by this rich Dane to do some math for him? Sure, I'll take it. And after a few years, they really weren't getting anywhere. They weren't making a lot of headway. And then Tycho Brahe dies, pretty unexpectedly. And after Tycho Brahe dies, Kepler got promoted and basically got Brahe's job as the royal astronomer for the Kingdom of Denmark, which really gives, when you've got a nice lofty title and a paycheck like that, then Kepler can really hunker down and get to work. And Kepler decides that he'll start on trying to figure out the motion of Mars before he goes and tries the other planets. And he tries to explain, he tries to figure out, how can I take these measurements of the motions of Mars, and how can I use these measurements to support the idea that Mars and the Earth go around the sun? And he's trying to make these numbers fit. He's fiddling with the numbers and trying to make them make sense in an orbit of the sun, and he just can't do it. He's pounding away at these numbers for 8 years, trying to show how the motion of Mars can support the idea that the planets go around the sun. For 8 years. And after that long, he realizes, well, there's one assumption that he's been making this whole time. Kepler had been assuming, like Brahe and everybody else at the time was that the motions of the planets were circular. Copernicus thought that the motions of the sun, or rather the motions of the Earth and all the other planets around the sun, were perfect circles. And that's the assumption that Kepler had been working under that entire time. And so eventually he says, well, what if the orbits of the planets are not perfect circles? What if the orbits of the planets are ellipses? And then everything clicks into place. Finally, he gets these measurements to work. And so Kepler ends up writing the first two of ultimately what would become his 3 laws of planetary motion. So by using these naked eye measurements of the planets, he's able to come up with 3 principles that describe how the planets go around the sun, not the Earth. Notice what I just said there. Kepler's laws of planetary motion describe how the planets go around the sun. Because the thing is, nobody knew why the planets go around the sun. today we know that the planets go around the sun because of gravity. But Newton hadn't been born yet. It would be decades longer. It wouldn't be for decades until Isaac Newton would be born and then grow up and formulate his theory of gravity. So Kepler's laws are describing how the planets orbit the sun, but they don't explain why the planets orbit the sun. And I make that distinction because Kepler's laws are kind of convoluted. They seem kind of long-winded, and the reason why Kepler's laws seem so peculiar is because Kepler doesn't know why the planets go around the sun. He's just saying, well, based on the way I watch the planets move, this seems to be how the planets go around the sun. So, I'm going to go through these first two laws really quick, and then we'll unpack these, okay? So, Kepler's first law says that the planets orbit the sun in elliptical orbits with the sun at one focus point. Kepler's second law says that if you draw a straight line between a planet and the sun, that line will sweep out equal areas in space during equal intervals of time. Now, what does this all mean? Okay, let's unpack this here real quick. If it's been a while since you've studied ellipses, that's okay. It pretty much has been for everybody. But remember, if you remember from probably high school geometry, what is an ellipse? An ellipse is this oval shape that is defined by these two fixed focus points. There are these two fixed focus points, and if you take a loop of string and a pencil, and if you hook that loop of string and pull the pencil taut between these 3 points, then if you pull that pencil and hold it taut, if you try to move and sweep out a line with that pencil, what you'll actually end up sweeping out is this oval shape. So that you end up with this oval shape that has a long axis along this way, called the major axis. The minor axis of the ellipse is the short axis here, and the shape of your ellipse is defined by where are your two fixed focus points, and how big are your major and minor axes. You can describe the shape of an ellipse in terms of what's called eccentricity, where if your eccentricity is 0, essentially what you're saying is that your ellipse is not stretched out at all. It's not elongated like this ellipse. What you have is an ellipse that is not elongated, it's not stretched out at all, so it's a circle. So a circle is an ellipse. This is the thing to remember. A circle is an ellipse. It's just an ellipse where both focus points are at the same place. And so if both of the nails, if both of the foci are right there, then your loop of string is actually just going like this. It's the radius of the circle, and then what shape does the pencil sweep out? It's a circle. So a circle is a special case of an ellipse, one where the two foci are at the same place, the two focus points are at the same place, and therefore your ellipse has an eccentricity of 0. If you pull the two focus points apart, then your ellipse is going to start becoming moderately elongated, or have a moderate eccentricity, and the farther apart you pull your two focus points, the more elongated, the more eccentric it becomes. Okay, so let's restate Kepler's first two laws then. All right. Kepler's first law says that the orbits of the planets are ellipses, so the planets always orbit the sun in an elliptical shape, specifically with the sun at one of the two focus points. So if this is the orbit of a planet, the sun has to be at this focus, or, remember, an ellipse always has two focus points, so the sun has to either be here or over here. And so, with this planet, the sun is over here. So, Kepler's first law, elliptical orbits with the sun at one focus. Kepler's second law says, if you draw a line, if you draw a line between the planet and the sun, then as the planet moves from here to here, that line will sweep out this area in space. Now, on this diagram it says that the area swept out takes 30 days. So if the planet takes 30 days to go from here to here, it'll sweep out this area. If the planet takes 30 days to go from here to here, it'll sweep out this area. And what Kepler's second law says is, if these two wedges take the same amount of time, which in this case is 30 days, if they take the same amount of time, then these two wedges have the same area. Like I said, Kepler's laws are kind of convoluted and roundabout, but let's think about this for a second. Why would this be? Let's use our physical intuition. Let's say what we know about motion and gravity that Kepler didn't know. How can we explain this? How can it be? How can it be? Oops. Oh, okay. How can it be that a planet takes the same amount of time to go this distance as it takes to go this distance? How can that be? How can the planet go this far in 30 days over here, but it only goes this far in another 30 days? If a planet is traveling a different distance in the same amount of time, in the same 30-day period, then it must be because the planet is traveling faster over here and slower over here. That way it takes in 30 days, it can go this far over here and that far over there. Now, why would that be? Why would a planet go faster over here and slower over here? Well, it must be because of the force. Right, let's use what Newton taught us here, which Kepler didn't know, is to say, when the planet is closer to the sun, the gravitational force between them is stronger. And if the gravitational force between them is stronger, then the planet is falling around the sun faster. And therefore, it travels a greater distance at a greater speed in the same amount of time. Out here, the planet, as the planet goes farther and farther and farther from the sun, it's going to travel slower and slower and slower until it gets all the way out here, as far from the sun as it can get. By the way, the points in a planet's orbit where they are closest and farthest from the sun are called perihelion and aphelion. So, when the planet is out here at aphelion, it's at its point farthest from the sun, it has slowed down such that it is going to travel a shorter distance in the same amount of time. The one thing that doesn't change, though, this is the important takeaway here. The important takeaway from Kepler's second law is, as a planet goes around the sun, everything is changing. The speed is changing. The distance from the sun is changing. The one thing that doesn't change is the area of the area that is swept out. The area of these two wedges stay the same. Is it straightforward and easy? No, it's a little weird, right? But that's the important takeaway here, is that how do you get these two wedges to be the same area? It has to be that when the planet is close to the sun, it orbits faster, and when it's farthest from the sun, it orbits slower. Fastest at perihelion, slowest at aphelion. Now let's see, what have I not covered? The major axis of the ellipse is the long axis, the axis that runs from perihelion through the two focus points and then to aphelion, so the long axis here. The minor axis is the short axis of the ellipse, and the half of the major axis, so from the center of the ellipse out to aphelion, or from the center to perihelion, that's half of the major axis, so it's called the semi-major axis. That'll become important here in just a second. The eccentricity is a number that describes how stretched or how squashed or how elongated the ellipse is. So the eccentricity value always runs from 0 to almost 1. So from 0 to 0.99999. If your eccentricity is 0, then it's not elongated at all. It's a perfect circle. And then as your eccentricity becomes a larger and larger fraction, then it's becoming more and more and more stretched out. The period of a planet's orbit is the time required for the planet to complete one orbit around the sun. So just remember that. The period of an orbit is the time for one orbit. That becomes important because after the success of his first two laws, Kepler then kept on working for a few more years, and he figured out that there's actually a third relationship. There's actually a third law that describes how planets orbit. And so what Kepler's third law says is that there's a simple relationship between the period of a planet's orbit and the semimajor axis of a planet's orbit. That the period squared equals the semimajor axis cubed when those two quantities are measured in convenient units, which is to say, the period, in this equation, the period is measured in years, and the semimajor axis is measured in astronomical units. What is the period? The period is the time for one orbit. What is the semimajor axis? Well, on the face of it, the semimajor axis is just half of the major axis. But the funny thing about elliptical orbits is, as the planet orbits around the sun, okay, sometimes it's close to the sun, sometimes it's far away, but if you calculate the average distance between the planet and the sun, the average distance, sometimes the planet is closer and moving faster, sometimes it's slower and farther away, but the averaged over one orbit, the average distance from the planet to the sun is exactly equal to the semimajor axis. So the major axis is the length from perihelion to aphelion, but half of that, from the center to perihelion or from the center to aphelion, that semimajor axis is essentially equal to average distance. So whenever I talk about the semimajor axis of an orbit, there's nothing more complicated than semimajor axis is just average orbital distance. It's the average distance between the planet and the sun. And so if you wanted to measure the distance between the planet and the sun, you would use astronomical units, like we've been doing so far. Such that when you take all of the planets that Kepler was studying, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, because those were the only planets that anybody knew about at this time, Uranus and Neptune hadn't been discovered yet because you can't see Uranus and Neptune with the naked eye. So the only planets that anybody knew about were Mercury through Saturn. But if you take all of these planets, when you calculate the period squared and the average orbital distance cubed, they're exactly equal to each other for all of the planets. Which means what? It means that the farther away a planet is from the sun, the longer it's going to take to orbit the sun, which intuitively makes sense. You know, if a planet is farther from the sun, it's going to take more time to orbit the sun. But specifically, those two properties of the orbit are related to each other like this. Now, why? Right? Why is it that p squared equals a cubed? Why is it that the period only depends on the orbital distance? And this works for anything orbiting the sun. This is true for planets. This is true for asteroids and comets and spaceships, and anything that's orbiting the sun is going to orbit the sun according to Kepler's 3 laws of planetary motion. When Kepler was doing it, he only thought about planets orbiting the sun, but it turns out we've discovered a whole bunch of things orbiting the sun, like planets and asteroids and such. Actually, it turns out that it's not just the sun, that anything orbiting anything orbits according to Kepler's 3 laws of planetary motion. But now, why is that? Why does everything orbit? Well, what's causing orbits? What is it that holds the moon in its orbit around the Earth, or the Earth in its orbit around the sun? It's gravity. And so gravity works the same everywhere. Right? Since gravity works the same everywhere, then anything orbiting under gravity should work the same. How does it work? According to Kepler's laws of motion. So Kepler figured this out. Kepler created these 3 laws to describe how planets orbit the sun, but nobody still knew why, just that they did. Decades later, when Newton figured out his theory of gravitation, there were some people who, justifiably, were skeptical. You know, Newton says, hey, I figured out how gravity worked. And some people said, well, if gravity does work the way you say, Isaac, well, then you should be able to explain why planets orbit the way Kepler's laws say they do, right? If gravity is what causes orbits, then your theory, your equation for the gravitational force should be able to explain why planets orbit the sun with elliptical orbits, sweeping out equal area in equal time, etc., etc. And Newton was actually one step ahead. Newton actually had already done that, and all he had to do was sort of copy down his notebook and say, oh yeah, here's the proof. With one extra thing. The thing that Kepler didn't know, but Newton had figured out, is that the gravitational force depends on mass. And so when Newton used his formula for gravitational force, when he tried to use this force to describe and to explain orbits, he was able to explain why planets' orbits are specifically elliptical and why the planet sweeps out equal area under equal time. When he came to deriving Kepler's third law, it turns out that because the gravitational force depends on mass, then how much time it takes a planet to orbit, depending on its distance, also the gravitational force depends on the distance, which in this case is a. So notice in Kepler's third law, the distance between the planet and the sun is a, the semimajor axis, whereas in Newton's equation it's r, the radial distance. These are just two ways of talking about the same thing, two ways of describing. R is the distance, a is the distance, the average distance, right? A is the average distance. So that the gravitational force, and since the gravitational force depends on mass and distance, the period does too. So this equation here is what you could call Newton's version of Kepler's third law, where, again, period is in years, the semimajor axis is in astronomical units, and M1 and M2, in this case, M1 and M2, the masses of the two objects that are orbiting each other, are in solar masses. So if you're trying to describe, or if you're trying to describe two objects that are orbiting around each other, M1 and M2 are orbiting each other. If these two objects are of similar mass, if their masses are close to each other, then you would do, the mass of the two objects combined, M1 plus M2. That's going to determine the period. In the case of planets, though, a planet has so much less mass than a star that if M1 is the mass of the star, if M1 is the mass of the sun, and if M2 is the mass of the Earth, if you take the mass of the sun and add the mass of the Earth, it's just the mass of the sun. Adding on the mass of a planet does not significantly change the total mass. So really, the only term here that's important is the mass of the star, which in this equation is M1, but we're going to simplify this to say, well, in this case, Newton's version of Kepler's third law is the mass of the star times p squared equals a cubed. And again, a is in astronomical units, p is in years, m, in this case, the ms, the mass of the star, is in solar masses. This is a good thing to remember. If we're talking about planets, then we can use the equation there on the bottom. If we're talking about two objects that orbit each other that have similar masses, like, say, binary stars. If it's two stars orbiting around each other, well, then the mass of star 1 plus the mass of star 2, you can't really neglect one of those terms. They're both significantly large masses. When M2 is a significantly small mass, like, say, the mass of a planet, then you can ignore that, and M1 is just the mass of the star, which we're calling capital M sub s down here. If we're talking about planets orbiting our sun, then the mass of the star is just 1. Right? The mass of the star is 1 solar mass, in which case 1 times p squared is just p squared, and then you have p squared equals a cubed, which is exactly what Kepler was talking about with his third law. Pretty soon in this class, we're going to start talking about alien planets. We're going to start talking about other planets that orbit around other stars, in which case we need to take the mass of the star into consideration. We might not be able to just say, well, the mass of the star is 1, because it might not be 1 solar mass. if you're an alien planet orbiting around a star with a different mass, you got to plug that mass in there in order to understand the period and the orbital distance of those exoplanets, of those alien planets. So that's going to come in handy pretty shortly here. So at this point in history, if we're looking through the history lesson of, for 2,000 years, Western civilization has taken it as a proven thing that the planets and the sun go around the Earth. And then Kepler and Brahe and Copernicus, they say, no, the planets and the Earth go around the sun, not the other way around. Kepler has these 3 laws that describe how the planets orbit the sun. At this point, still nobody knows why, because Newton hasn't been born yet, but Kepler has these 3 laws that do a very nice job of mathematically describing how the planets can orbit the sun, not the Earth. There's no proof, though. Right? You know, Kepler has written these 3 laws saying, yes, I can explain how the planets go around the sun and not the Earth, but having some nice equations that describe things well is not the same as proof. There's essentially a tie. If there's a debate between do the planets go around the Earth or do the planets go around the sun, after Kepler wrote his laws, we've got a tie. We don't have the evidence yet to prove one way or the other, to prove that the planets go around the Earth or do they go around the sun. So enter Galileo. Right? Galileo did a lot in his career. Right? Galileo was the first astronomer to buy these newfangled telescopes that were coming out of the Dutch lens works. And he builds a telescope, and he takes his newfangled telescope and points it at the sky and records what he sees. And not only, like any good scientist, not only does he see new things that no one has ever seen before, but he writes it down and tells everybody about it. So he writes this book called The Starry Messenger, and he publishes this book and says, hey, look at all the things that I see in my telescope, and if you build a telescope, this is what you'll see too. He sees that there are mountains and valleys and craters on the moon. You know, if you look at the moon with the naked eye, it looks pretty smooth to the naked eye, but with a telescope you can see all of these features that look very terrestrial, almost like the moon is a big rock just like the Earth is, which nobody knew at the time. He pointed his telescope at the Milky Way in the sky, and it turns out that when you have the resolving power of a telescope, that you can make out that the Milky Way is made of what? It's made of just even more stars. Just stars that are very, very far away, so that you can't see the individual stars the way you can see nearby stars with the naked eye. This was a huge deal. Right? With the telescope, you can see much deeper into the galaxy and see that as far away as you look, there's just even more stars. And all of a sudden, with Newton's work and with other people using telescopes at the time, people realized, all of a sudden the universe is bigger and deeper than anybody knew. Galileo pointed his telescope at Jupiter, and he saw that Jupiter always has these 4 little companions around it. Here's a picture with a decent-sized telescope today. That, you know, what Galileo saw as these 4 little lights that were always hanging around Jupiter were moons. Galileo discovered the 4 largest moons of Jupiter. Today we call those 4 moons the Galilean moons, because Galileo discovered them in the early 1600s. These were the first moons beyond Earth's moon. Right? Everybody knew about Earth's moon because it's easy to see. These were the first moons ever known about around another planet. So these are a huge deal. So Galileo publishes his book, he becomes famous as the discoverer of all these new things, he gets a little bit of money, he gets a good job at the University of Pisa, and he keeps on going. And as he keeps working with his telescope, he points his telescope at Saturn, and, well, he thinks he discovers 2 giant moons on either side of Saturn. It turns out he didn't discover moons, he discovered the rings of Saturn. He pointed his telescope at the sun, which don't look straight at the sun, always a bad idea. But when Galileo did that, he saw that there are little dark spots on the surface of the sun, that the sun is not uniformly glowing and shining, that there are these little dark spots on the surface of the sun, which we call them sunspots. And then he pointed his telescope at Venus, and he discovered that Venus has phases much like the moon does. And Galileo knows this is a big deal, because there's still this tie. Which is it? Do the planets go around the Earth? Right? This is the theory that was put forward from ancient Greece. This is the major idea that a Greek by the name of Ptolemy put forward in the 2nd century AD, I think. So again, for the better part of 2,000 years, people thought, like, okay, so the planets are going in these orbits, in these circular orbits around the Earth. So here's Venus, it's orbiting around the Earth, and it's moving like this, with these little loops, which is how Ptolemy was able to describe the retrograde motion. And here's the sun going around the Earth. And if Venus and the sun are both orbiting around the Earth like this, well then, yeah, you would expect that Venus has phases, right? When Venus is here and here, then there's no sunlight shining on the side of Venus that you can see, and therefore Venus has a new phase, much like a new moon. And when Venus is here or here, then the sunlight shines on Venus, it reflects back to the Earth, so that Venus would have crescent phases, like a crescent moon. So, if the Earth is the center of the universe, and the planets and the sun are orbiting around like this, then what you would see is that Venus would have new phases and crescent phases, another new phase, another crescent phase. That's it. If, on the other hand, if Copernicus and Kepler are right, then here's the sun sitting at the center, here's Venus going around the sun, here's the Earth going around the sun, and then what phases would you see? Well, from Earth's point of view, if Venus is here, it would have a new phase, a crescent phase, a quarter phase, a gibbous phase, and a full phase. So, here's the evidence that can break the tie, right? If you look at Venus and Venus only has new phases and crescent phases, then Venus and the sun must be going around the Earth. The Earth is the center of the universe. If Venus has new crescent, quarter, gibbous, and full phases, that's the smoking gun. That's the proof that the planets go around the sun and not the Earth. And if you watch Venus over the course of several months, here's a picture taken with a decent telescope from a few years ago to illustrate what Galileo saw. Yeah, sure enough, Venus has new phases, crescent phases, quarter phases, gibbous phases, and it's pretty hard to take a picture of Venus when it's in a full phase, because when Venus is in its full phase, it's behind the sun, and it's only up during the daytime, so it's hard to take those pictures. But Galileo, by watching the phases of Venus, Galileo is the one that's able to publish this discovery and break the tie and say, oh no, here is the proof, the absolute proof, that the planets must be going around the sun, not the Earth. So this period of, well, the better part of the mid-16th to mid-17th century is called the Copernican Revolution, because it is a scientific revolution in the way that people thought about Earth's place in the universe and humanity's place in the universe. That before Copernicus, everyone took it as a given, going back to ancient Greece and Aristotle and Ptolemy, that the Earth is sitting still and the planets might be making these little loops around the Earth, which is how they tried to explain retrograde motion, but otherwise, no, the planets go around the Earth, the sun and the moon go around the Earth, everything revolves around the Earth. And then little by little, one person has an idea and gives it to somebody else. You know, Copernicus has an idea and passes it along to Brahe and Kepler, and then Kepler passes along to Galileo, and Galileo passes his ideas along to Newton, and Newton is the one that puts this all together to create a unified theory of motion and gravity. To not only throw out an argument as to, like, well, why I think the planets go around the sun. But the absolute proof, all you got to do is point your telescope at Venus and watch it for a few months, and you can see, no, the only way to explain the phases of Venus is in a universe where the planets orbit the sun and not the Earth. People throw around the term scientific revolution kind of willy-nilly sometimes because science and technology are advancing so fast that it seems like every discovery is a revolution. And it's really not. A scientific revolution is a big deal. A scientific revolution is where people thought the universe was one way, and it turns out the universe that they live in, the universe that we've been living in the whole time, is completely different. What does it take? What have we been talking about from the beginning of the semester? What we've been saying is, if you think you've got a good theory, if you think you have a good explanation for the way the universe works, you need the evidence. That a good scientific idea lives or dies by the quality of its evidence. And Galileo was finally the one, because he had the telescope, because he had an instrument that was better than the naked eye, you can get the evidence that you can't get with the naked eye. The evidence that Venus's phases are only explicable in a universe where planets orbit stars, not the other way around. A generation later, Newton would come along and add his perspective, his unique, unique, yeah. I mean, he had a unique view of how mathematical the universe must be. And it's really that generation, the shift from Galileo to Newton, where people went from saying, well, I think things move around like this, which was sort of the Copernicus, Kepler, Galileo view of things. You know, Kepler and Galileo were pretty good at trying to make measurements and calculate quantities, but once Galileo really proved that planets move around the sun, then Newton could come along, pick up from where Galileo left off, and said, okay, well, since we know this is how planets orbit, let's explain it. And this is how Newton was able to create his universal theory of gravity, to say, okay, gravity isn't just about the moon around the Earth or the Earth around the sun, but gravity is a property of all matter based on their mass. And that really signifies the beginning of physics as a field of science, to say, well, everything is quantifiable. Everything can be, every seemingly complicated system in the universe can be reduced down to its simple equations that should be able to explain, hopefully, everything. And like we were talking about when we were talking about motion and gravity, if you've got the simple equations, you can explain a lot with some very basic ideas. And that concept, the concept that understanding the universe is fundamentally a simple thing and does not require long, convoluted disquisitions, that is a revolution. And that is a revolution that created the Enlightenment and the age of learning that we have all inherited. So, on that note, I will let you go. I hope this is making some sense. It definitely takes a little getting used to. It's a little complicated and takes some practice. So we will get some practice back in class, so that this hopefully makes even more sense, because this is going to help us understand how all planets work for the rest of the semester. All right, thanks everybody. Have a good one.